You have used the language model today and it offered you the next word and it was probably right. And this is the entire job, and every model does this and nothing else. So a chat GPT writing an essay is just repeating the same exercise a few thousands of times. You give in a text as an input and it predicts what comes next. Okay. Well, in this video, we'll make a model that does the exact same task. We give in a text and it predicts what comes next. Well, before moving on, I have a few promises to make to all of you. Number one is that after watching this series, you'll have a complete understanding of how a GPT or any other large language model works inside out. Promise number two is that you won't only understand it, but you'll understand it from the first principles. You'll understand the why behind every decision that we'll make. And because that's the point of this channel, is that teaching you AI from the first principles. I just expect you to know the basics of Python, and you just need to focus and you will understand. And the last promise as well is that it is going to be easy. With that, let's begin. So let's start with what a simplest language model that we can build. So let me go to my code. So here I've built the entire course, which has all the files which we'll go through one by one in the series. Let's start with the problem that we are dealing with. So I've just run the file in the terminal. So don't worry about the code right now. If you know the Python, it's easy for you. Let's start. Now, a language model is just a next word guesser. So what's the simplest model that we can build? Simplest thing we can do is just start predicting randomly. That's the simplest thing we can do. So I did that, and the result I got was this: table, greeted, slow, tower, honey, beggar. And as expected, it makes no sense. I did the quick grammar check and it came out 0%. So it absolutely makes no sense because we are predicting randomly. Well, let me also tell you that for the sake of simplicity, I'm using a 500 word language. So the vocabulary size is only 500 words. Now, to just give you the idea of the scale, if I go to this tab where I've already searched about GPT, vocab size of latest GPT models. So you'd see GPT-3 had 50,000 tokens, GPT-4 1 lakh, GPT-4 latest has roughly 2 lakh tokens. Well, you must be wondering, what are these tokens? I was mentioning words earlier, now it's tokens. So these large language models, they divide a word into subwords, and these subwords are repetitive in many other words of the English language, so that we can reuse it and we can use these subwords to make other words. That's why we break single word into subwords. Well, this is a website which is the OpenAI website. You can go to that URL. Here, if I put in some random text, you can see how those words convert into tokens. So if I were to zoom in, many words map. So here each word is a token, but if you come across this word, indivisible, that breaks down into two subwords, indiv and isible, right? So you get the idea of tokens. Let's say this was GPT-5, but if I go to GPT-3, you can see indivisible is broken down into three subwords: ind, ind, iv, and isible. Okay, so that's the idea of token, and this is a very crucial step of our language modeling. But for the sake of simplicity, I'll skip this step right now. So what I'll do is I'll consider each word as a token. So I hope that's okay for you, but I promise that I'll make a separate video on tokenization. I made tons of promises in the first 5 minutes of the video. But anyways, let's go back. So our vocabulary size is 500, and using those same 500 words, the total length of our text becomes roughly around 1,63,000. Okay. Now, so I randomly predicted the words. I got very basic or not even a single legal statement. Okay. Now, this is the bottom line. So now every model we'll make has to be a better version from here. So this is the least that we could have done. Okay. Now let's keep improving it. So now what comes in my mind is I'll go through the entire text word by word and I'll look at two words at a time. So for example, I have the word cat. I'll see what is the most common word which is followed by cat. And I did that, so I got full stop is followed by cat 99 times. The word to word followed by cat 6 times. Okay, so this was the data about cat. I'll do the same exercise for all the 500 words. So what this data tells me is that most probably the word cat would be followed by a full stop, right? So now we can take this data, and based on this we can start making predictions. So I want you to visualize this. So I'll just quickly run this command, just open wiz.html, and here we go, right? Let me do this. Perfect. So the model that we have just trained is called a bigram model, and simply it's just a counting model. Now how I want you to imagine is, imagine a book with 500 pages. Each page represents a word. So let's say page 74 represents cat. If I go to other word, 84 represents chicken, and so on. Now once I go to any particular page, here I have this data. 61% chances that it will be followed by a full stop, 2% by the word behind, and so on. Correct? So I have this distribution. Now using this data, I'll make my next prediction. So what do you think should be my next word after the word coin here? So will I always predict the most percentage word or the most probable word? No, because that won't be a good model, because we'll be predicting the same thing again and again. So instead of simply predicting the most probable word, we'll roll a weighted die. And what it does, it assigns weight to each of the word, and basically more the percentage, the more weight is assigned. And now we'll throw a die and we'll see what comes the next word. So let me roll it, and there we go, we got a full stop. Okay, now the moment we go to the page 0, which represents full stop, I have another distribution. The word every has 16% chances, right? So I will not predict the word every all the time. I'll roll a die. Let me do it, and I got I simply got A. Now let's go back to page A. We got the data, roll the die, predict the next word, and we got this. So far coin, full stop, a hungry. Roll the die, got the message, a hungry beaver. Roll the die, and we get the next word. So what do we get? A hungry beaver buried. Okay, so first of all, congrats, we made a simple model which predicts the next word. But surely this model is not the best one. It has many problems, and let's look at what problems do we have now. So in the code which I have here, I predicted some sentences using the same model, and look what I got here. That cloud, some sparrow, this wet goose, every book, one village around another neighbor. Okay, well, I did a grammar check and it came out 22%. Okay, so we did make some progress, but still 22%. Now what's wrong here? It's very simple, that every sentence is fine as long as you're looking at the two adjacent words. The moment you read the whole thing, it makes no sense. For example, the misty cloud behind every blue honey makes no sense. But let's say cloud behind every blue or blue honey kind of makes sense, right? So the two words make sense because that's how we trained our model. We looked at two words together and we collected the data. Now, how do we fix this? Well, the fix is going to be very simple, is that we look at all the previous words and not just one. Right now, we are only looking at the last word. Let's say we looked at cat. We went to that page number, we saw the distribution and predicted the next word, and so on. But we did not see what came before cat, what was the context before cat, right? So the fix is we have to start looking at all the previous words and understand the context. Right now, our model is only a counting model. Literally, we didn't use any AI, no neural networks. It was just a counting machine, and we collected data and we predicted words. Now, in order to improve this, we have to follow certain steps. Number one, we have to make machine understand text, but it does not understand text directly. So we have to convert text into numbers, and that is a very crucial step, and that is called embedding, and we'll look into that right now. And I'll quickly tell you what comes after. Once we have done embedding, we need a way to learn from data rather than tally. So this currently is just a tally model, a counting model. So we have to make sure that our model learns from the data that we have, and then we'll do some averaging. We'll take the averages of all the previous words, and then we'll apply the attention. I'm pretty sure that you have heard this term before. If not, that's okay. And then we'll also include the positional embeddings and all that. Right now, you don't need to worry about all those, but what you've understood is that we made our first model. Now let's convert text into numbers. That is going to be our next step. Perfect. Now, in order to convert words into numbers, what's the simplest thing we can do? Yes, just map each word with an integer. So right here, I have, let's say, all my 500 words written in the alphabetical order, starting from a full stop, then A, accepted, across, and so on. Let's say dot is mapped with 0, A is mapped with 1, accepted is mapped with 2, and so on. And we have converted words into numbers. But is this okay, or will this work? Let's see. So let me open the code. So as you can see, I made this lookup table where cat is mapped with 74, dog with 130, and so on. Now the real question is, does this number mean anything to the machine? For example, cat is 74 and dog is 130, and so does this mean dog is 130 bigger than cat, which is 74? Maybe not. And also another example, let's say cat plus dog, which is 74 plus 130, 204. Now 204 is mapped with the word harbor. So does this make any sense where we add cat and dog and we get harbor? Definitely not. Now, how do we solve this problem? Because right now these numbers are simply labels. They don't mean anything. Now, a simple way to fix this is that represent each word using multiple numbers and not just a single number. And each of that number will mean or will add some extra information so that we can get the complete context of that one particular word. I'll give you a quick example. How does computer understand colors? We write the RGB values. R represents red, then green, then blue. And each value is between 0 and 255. Right? And different combinations of these numbers gives us different colors. So here we have represented each color in form of numbers, and each number represents or adds some extra information, right? So that's the whole idea. We'll do the exact same thing. So let me run the next file here, which is the embedding file. Okay, perfect. So what we can imagine, so here I have made a three-dimensional embedding. So I'm using 3 numbers to represent each word. So let's say each of the number says how alive I am, action, and the third one is big. So right now I'm writing it, I'm assigning numbers myself, but we'll do it automatically for all the 500 numbers or 500 words. So cat, alive, yes, 0.9, action, maybe no, big, we gave it a negative. Let's look at something as castle. Is it alive? So we give it a negative score. Action, no. How big? Yes, so we give it a good positive score. Now a better way to visualize this is using this 2D plane. Here we have, right? So I showed you the example of 3 dimensions. Let's assume 2 dimensions just for easier visualization. So the horizontal axis represents alive or aliveness, and the vertical represents the size or how big the object is. So dog lies somewhere here. So it is alive, but it's small. And the castle, so it's not alive, but it is big, right? So you get the idea. Now here, we just use 2 dimensions. Now to give you the idea of scale, for example, GPT-4 uses 12,288 dimensions, right? So imagine the scale. The code I have written, I've used 16 dimensions to represent each word. Correct? But as we move further and further, it becomes very difficult to visualize it, right? You cannot visualize even 4 dimensions, right? So 2D is okay, 3D is okay, but after that we cannot visualize. So I hope you get the idea of embedding. We are simply representing each word with multiple numbers, and each number means something. Now let's go back to the code. Okay, now comes something called a similarity check. So we have, now you can start imagining each word as a vector, because multiple, let's say I showed you the example of 2 dimensions, so you can imagine it as a 2-dimensional vector or a 16-dimensional vector, or in the GPT case it's 12,000 roughly dimensional vector. Okay, now we have to check the similarity of these vectors. How do we do that? So for that, you must have heard of something called as cosine similarity, right? So it's a metric used to measure how similar two vectors are by finding the cosine of the angle between them. So simply what we do is we do 2 steps. We find the dot products and we find the magnitudes of both the vectors, and to find the similarity we divide the dot product by the product of these lengths or by the product of these magnitudes. That gives us how similar two vectors are. Correct? So to help you visualize it, let's say I have cat and dog, these 2 vectors. Now look at the similarity. They are roughly in the same direction, so I get a positive score, plus 0.98, which is a really high score. It means they are very similar. I choose something called let's say castle. Now definitely this is a negative score because they are like roughly in the opposite directions. So you get the idea. Let's say if I use castle and castle, the score will be positive 1. So the exact match means we are like the same vectors, so it gives you plus 1. Exact opposite would give you minus 1. So the values lies in this range, -1 to 1. So now we can also measure how similar these vectors are. That is also good. Now one more thing is we have to start getting used to writing tensors or matrices. So basically in the field of AI or machine learning, we use matrices a lot because it's easier to represent these multi-dimensional numbers, and also it's handy in doing the arithmetic at once. You can do multiple matrix multiplication at once if you are using a GPU, so it's much faster, right? So let's say I have this embedding table. So imagine I have one sentence where I have 5 words. So only keep these 5 words in your mind. I have the embedding table of these 5 words, right? So the dimension of this table is 5 cross 3, right? 5 rows each for one word, and each word is represented using 3 numbers. So 5 cross 3. Now here I have written something called as one hot encoding. So let's say I want the embeddings of the third word. So I'll put 1 at the third position, rest all 0. Now I'll multiply this matrix or this vector with my embedding matrix, and once I multiply, so I hope you know how this matrix multiplication work, where we multiply each row with each column. So if I take this row 0 0 1 0 0 and multiply with each column, what do I get? The first column would give me 0 0 0.8 0 0, so I only get 0.8 out of there, and similarly I'll do the same for next 2 rows. So if I multiply these, what do I get? Right, I get, after multiplying, I get this particular row. So I've ultimately what I've done is just taken out the embedding of that one particular word, but I'm using matrix multiplication to get out that embedding. This will become more handy as we move further and further into this course, but right now I hope you get the basic idea. Right now let's do a quick summarization of what we have done till now, right? So here we have, as you can see, this table here. This is 500 cross 16. So there are 500 rows, each row for each word, and then each word is represented using 16 numbers. Perfect. So total, if you multiply, we have 8,000 numbers, and as you can see, each of this number will be learned as we'll train our neural network. 16 is the dimension of our model. That's why it's represented as d_model. The research paper, attention is all you need, uses 512 dimensions. GPT-3 uses roughly 12,000 and we are using 16 dimensions. And now let's take out one particular row which represents cat right now, but right now it's totally unrelated. It's random numbers, and dog and cat, they are totally unrelated. And the whole idea of training would be to come up with the best values of these numbers. So a quick summary, we made a next word guesser because that's how all the language models work. Then we said, okay, we'll represent each word with a number, and we mapped each word with a single integer. But it turned out one number carries nothing. So we used a list of numbers to represent each word. And right now we have assigned it a random number. So it's total mess. It's a random noise and it's a random cluster. So the training loop will fix this. After the training, the embedding would look like something like this. So the similar words will form a cluster together. So a cat and dog, they'll drift together in their own, in the same direction. So I hope you get the idea of what are we building and what we have done till now. Perfect. So I guess that's it for this video. I hope you understood. This was a very basic lecture, and as we move further and further, it will get more and more interesting. And I am pretty sure this one was easy to follow for all of you. And as I mentioned earlier, I don't accept sorry for the interruption, and as I mentioned earlier, that I don't expect you to have any knowledge prior to watching these videos. I teach from the very first principles. If you do like it, feel free to subscribe. I'll be uploading many more videos related to AI, machine learning, and various other concepts. If you have any particular doubt, let me know in the comment box below. Please do check out the code and other visualizations. I'll share the HTML files and all the other stuff which would help you learn the concepts better and better. That's it for this particular video. My name is Divyansh and signing off from this video. By the way, this right is from the ring light, so don't mind it from the next video onwards. That's it. Thank you very much.